As far as how the lecture is organized, it's pretty awful right now just because I didn't have time to go through and get it as organized as I would like because I spent all the time grading your exam. So in general, there are 12 sections within the textbook. I attempted to go through and kind of rank how the lecture is going to move through those sections and how the textbook moves through them. So the numbers are each of the individual sections. You'll see we're kind of going in order until we hit kind of the midway point, and then I kind of shuffled things around. Okay? Homework problems or textbook problems. The sapling and what will be the connect for chapter 15 are all math involved. So you got to come up with some number answer for pretty much everything. Okay? That said, when it comes to calculators, I'm not a fan of calculators. I'd like some non-calculation type questions, some approximation things. So the textbook questions I would highly, highly, highly recommend. Okay? These are the types of problems that I like to ask on an exam because you don't have to involve the calculator. It's just kind of a thought process game. Okay? So I would take a look, or highly recommend that you look at these questions, kind of go through and do those. You shouldn't have to use a calculator for any of them. Okay? I don't think any of them required it. Okay? I haven't posted those numbers yet to Canvas. I think I just picked those out this morning. Okay? So I will get those posted to the Canvas homework running tab so you've got access to all of them. Okay? So chapter 14, we looked at an equilibrium constant. We could solve for equilibrium concentrations. Okay? Or if we were given equilibrium concentrations, we could solve for the equilibrium constant. Okay? When we move into chapter 15, we're doing effectively the same thing, except now instead of looking at general reactions, we're looking at very particular reactions. So in chapter 15, an equilibrium constant, we can solve for the concentration of H+. Well, that's the same thing as we did in chapter 14. When we look at the other thing we could do, given a concentration of H+, we could solve for the equilibrium constant. Okay? All we've done is changed the terminology around, but we are doing the exact same types of calculations, the exact same manipulations. Okay? It's very easy to think that it's all new material and then get lost or bogged down in all of that information. Okay? It is the same stuff. We're just calling it by a different name. Okay? And I'll keep trying to go back to this idea that it is the same thing that you've already learned. It's just a new application of it. Okay? So since it's all new or all the same, what would we hope happens to the exam average? It should hopefully go up. Okay? That said, the exam average last semester stayed about the same. Okay? It's pretty much a 65 as well. Okay? So you're now aware of what happened last semester. You're aware that we're running the same material. Hopefully that will help you actually improve, and you can do better than last semester. That's what I'd really like to see. Okay? It's nice to see people improve over the past. Okay? So, same material. In general, we want to kind of go back and review a little bit, okay, and step away from it. So when we looked at equilibrium, we had general reactions, and we could go through and determine different equilibrium concentrations of our products or reactants. Okay, so we could look at this reaction type. In this case, it's a double replacement. Okay. So what phase would we typically include in all of this? Okay, aqueous. So we could tag in aqueous, and we would show that by saying parentheses aqueous. Okay. So just like we did with our equilibrium constant, we're still going to work with those in the acid-base chapter. Okay? And in fact, both chapter 15 and 16 are going to do the same things. Okay? Why do we pick aqueous? Out of curiosity. What's that? Yeah. Water is the most common solvent. So water is something that we'll typically run our reactions in. Okay? It's the easiest thing to get a hold of. That's where all of our chemistry will occur. Okay? Or where the majority of our chemistry will occur. We're going to actually expound upon that idea a little bit more and try and see how the chemistry of water actually impacts our acid-base chapter. Okay? So how do we know it was a reaction? I do a very good job of this one. What's that? Well, in this case, products do change. Would you be able to tell that a reaction actually occurred in this case? I'm going to go all the way. This is definitely 151, hardcore review on this. Well, we know it's a double replacement because I drew it. But if we did this reaction in a beaker, we'd have to see some physical observable. Okay? Color change, different phase. In this case, all of these are aqueous, so that makes it a little bit more difficult to determine what's actually happening here. So we would look for these changes in phase, we could look for changes in temperature, and hope we would see those. Okay? One of the big ones that we could go back to would be solubility rules. Okay? So if we saw a precipitate form. Okay? So that's one of the helpful observables when trying to deal with these. So, just to be obnoxious, let's go back and look at our solubility rules. You guys all have those solubility rules memorized, right? Oh, yeah. Okay. I only have one solubility rule memorized. Anybody know which one? The very first one. And actually, that's a lie. It's actually the very first of the very first one. The only one I have memorized is 1A. Okay? Which, as far as we're concerned with acids and bases, is pretty much all we need. Okay? We will go back and look at these a couple times. You should be aware of both Rule 1A and B. The rest of those we'll worry about when we get into Chapter 15, and we will have to see them in Chapter 15. Okay? Again, we won't have to have those memorized. We just need to be kind of familiar with where they are and what they are. Okay? So what happens when we add the following species into water? So we're going to draw out a balanced equation. What does sodium chloride look like? We get NaCl. Okay? And we could look at breaking this down into a couple different ways. Let's go ahead and look at the long way first. If we start with sodium chloride, okay, what phase does sodium chloride start as? A solid. So we could go through and say it's sodium chloride solid. We add water to it. What happens? That's where we're going to skip to in a second. It's the first thing that happens. It dissolves. How do we show sodium chloride dissolve? No, that would be dissociating. If it dissolves, so it's sodium chloride aqueous. Okay? Then what happens? Now where everybody wanted to go to. Now we can look at it breaking up. How do we know it breaks up into Na plus and Cl minus? What's that? Good answer on that. We could go through and detect the electrical conductivity of the solution. If there's no ions in solution, we wouldn't expect any electrical conduction. Now that we have ions, we would expect electrical conduction. So that's an experimental way to do it. How else could we do it?
Solubility rules.
We go back to our solubility rules. Solubility rule 1A. Anything with a group 1 element. Where's our group 1? Right underneath hydrogen. And we've got sodium underneath that. Means it's soluble. We're looking at it dissociating into our ions. Okay? Why bother to go through all of this? Okay? When we look at an overall reaction, typically the only thing that we summarize or that we evaluate is that last step. Okay? That's how most reactions get written out. One of the things that will become important to realize is that aqueous means that water is also present. Okay? Water is participating in this reaction. So that if we now shift to say something else like HCl, what happens? HCl starts as what phase? It's an acid, that's not a phase. Gas. HCl is a gas, one of the reasons why it's kind of dangerous. And if you jump up to highly concentrated solutions and you heat them, what happens to the solubility of HCl? Decreases, and we see HCl gas come off the top of that. Not particularly pleasant. Okay? So HCl is typically in a gas phase. What happens when we add that to water? First step, it dissolves. Next step, okay, we could look at it dissociating into the ions. Okay, how would we know it dissociates into the ions? We could go back to our solubility rules and see that, yes, that matches. We would expect this to completely dissociate into our ions for multiple reasons. Group 1A cations, hydrogen's a little bit weird. We can't run solely on that one. But according to Group 1A, or Rule 1A, we would expect it to go into our ions. If we take a look at Rule 2A, anything with chloride, bromide, or iodide is soluble as well. So we got two rules saying that we dissociate into our ions. Okay? So we could now look at it in this respect. Okay? So HCl gives up that H plus and Cl minus. How stable is H plus? Those of you in lab might be able to answer this question a little bit better. More or less stable than HCl? Less because it's charged. Okay? So what we want to do is try and stabilize that charge as best as possible. We could have chloride come back and stabilize it, except chloride's not really good at stabilizing. That's why it fell apart. So we'd have to find something else to stabilize it. What's that something else? We could look at water. I think I got enough space to squeeze this in. So what we can do is say, hey, instead of starting with our gas, let's actually start off with water. What's special about the Lewis structure of water, particularly around that oxygen? What did I just draw on? Lone pairs. What's special? Lone pairs of what? Electrons. What charge is an electron? Negative. What would that negative need to stabilize it? A positive charge, say from our hydrogen. We could draw this out as H3O plus and Cl minus. Okay. Which brings up an interesting occurrence, okay, or something to observe here. H plus versus H3O plus. What's the relationship? Effectively the same thing. Okay? So depending on what phase we're in, we might call it H plus versus H3O plus. If we're in water, we'd end up calling it H3O plus. Okay? Or hydronium ion versus hydrogen ion. Unfortunately, one of the things that we're going to find throughout this semester, I tend to be inconsistent in my usage of them. We are always in a water solution, so if I write H plus, what am I implying? H3O plus. Okay? So those two can be used interchangeably. Okay? If we look at this reaction, we had aqueous going to aqueous. No color change, no physical observable. So how did we know we got a reaction here? Think back way, way long ago. You mixed in, say, HCl gas. Somehow you got a hold of HCl gas and you put it into water. Said, oh, there's no reaction. How do you find out there's something reactive in there? Okay, you get your poor slave to stick their finger in it. Okay? Or you find some pool boy by the street. Hey, come out, stick your finger in this. Tell me what it feels like. Okay? And they find out, oh, there's actually something in there. Something actually happened with this. Okay? Which is really, really crappy, but that's how science started. Okay? You're too scared to get yourself burned, and you make somebody else do it for you. Oh, don't worry, that's just water. Okay? Don't do that anymore. That's a bad thing. Okay? So we can kind of visualize this. So in the process of doing this, the original person that discovered this said, you know what, there's something reactive in this solution. That is coming from the H+. Why did they say it came from the H+ and not the Cl-? Did you write down the previous equation, the sodium chloride? That turned into what ions? Sodium ions and chloride ions. We run that same little technique. Hey, can you stick your finger in this? What happens? Nothing. Okay, so what does that mean? The ions that came from sodium and chloride, or sodium chloride, have no real effect. But the ions that come from HCl do have an effect. What does that mean? Well, when we get to our ions, the chloride, as we just saw in the sodium chloride, is benign, completely useless, or non-reactive. What does that mean? H+. So this first person went through and said, you know what? H+ is my reactive species. Okay, that's the dangerous thing. Okay? I want to give a name to that. What name did he give it? Gave it acid. Said that solution was acidic. So what he was looking at is just how this species interacted with water to generate some powerful agent. Just leave it at that. Okay? He also went through, and tried it again with sodium hydroxide. Okay, you all confident with the whole sodium hydroxide solid plus water goes to aqueous, goes to the ions? Okay with that? So we'll abbreviate. We'll start with our water as a liquid plus our sodium hydroxide, which we'll say was aqueous, goes into the ions, Na plus, and OH minus. Okay, this one's a little bit more interesting. Sodium plus, was that particularly reactive? No, we saw that back in the sodium chloride, stuck our finger in that, no burning. Okay? Sodium hydroxide, when we stick our finger in this one, do we get a burn? Sodium hydroxide is known as what kind of a species? It's a base. When you stick your finger in a strong base, what happens? It burns. Okay? Not particularly a good thing to do. Okay? So we went through and said that this species was also reactive. So we said maybe we can come up with a way to stabilize it. Okay? Maybe water's coming in just like it did in the case of HCl. Okay? So we said the reactive species here is hydroxide. What does that hydroxide need to stabilize? It would need something positive. Okay? Water brought in electrons, but what else does it bring in? Brings in those hydrogens. So we could go through the assumption and say, okay, maybe this OH minus picks up a hydrogen. I can accept that. Let's go ahead and say it does that. So it picks up one of those hydrogens. What happens to H2O? Becomes OH minus. Net result, bases are a little bit easier to work with than acids as far as our reactions go. Our bases we can dissociate immediately into sodium ion and hydroxide. We don't have to add this extra water step because we end up getting the exact same result. Okay? So this person went through and said this was dangerous. What species was dangerous in this solution? The hydroxide. Came up with it. It was a slightly different burning sensation than the first one, so they had to come up with a different name. Okay? In this case, we came up with base. Okay, so the initial observations with these was made by Arrhenius. Okay, and he came up with some rules. We look at when we take an individual species and we dissolve it in water, if we see H plus ions or H3O plus show up in solutions, classify that as an acid. If we see OH minus show up in solution, classify that as a base. Okay, for those of you frantically writing this down, please stop. This definition is awful. Okay? One of the things that's nice about chemistry, and in particular organic chemistry, what we want is something to apply to all reactions. We want a definition that we can use that explains acid-base chemistry, explains combustion chemistry, explains double replacements. When we look at this definition, This definition only allows us to look at what? H plus and OH minus. If it doesn't give you OH minus, we have no idea about our definition. We can't apply that definition to anything else. Okay? And that happened to be the first development. They went through and took some things that don't seem to give OH minus right away or aren't part of the structure. Okay? And in that case, they somehow still generate OH minus. We have to come up with some way to explain that. Okay, we already talked about that. This is where Bronsted-Lowry came through and tweaked the definitions. Instead of it looking at H plus and OH minus, so two entirely different species, tried to simplify. Simplified it to H plus still. So if we generate H plus, we get acids, but then we look at our counter. If it can accept H plus, it's a base. What do you mean accept? What kind of a species would accept H plus or react with it? Anything negative, because H plus is positive. So what we can now do is kind of branch out and expand our definition a little bit. Okay? Unfortunately, this only expands it a little bit, and it doesn't apply well to all chemistry. Okay? We'll look at that all chemistry definition a little bit later on. Unfortunately, we won't deal with it this semester because a lot of the calculations that we end up doing, equilibrium constants and all of that, come back to our standard Bronsted-Lowry definitions. Okay? These two, okay? Our acids and bases being H plus donors and acceptors. Okay? So the big definition that you absolutely need to be able to do and manipulate would be this first one here. And since I don't remember what's on the next slide, we'll tap it and maybe go backwards. Yep, we'll go backwards. Okay? So let's try and get an idea on structure. Okay? So very few times we ever get to kind of not or avoid mathematics. This happens to be one of them. So if we're going to look at an individual structure, it might be nice to be able to look at it and say that is an acid, that is a base, depending on what we see. Okay? So what things would you look for in each of these cases? We already talked about some of them. So it was a big hint. Let me give you I think I got the formula right on that one. Most of those are strong acids because I've got those memorized, but one of them isn't. Why do you know those are all acids? They have the H. Okay? So if we're going to look at an individual structure, one of the big red flags for it to be an acid would be hydrogen. Why do we need a hydrogen? Our definition says H plus donor. If you don't have hydrogen, can you donate hydrogen? Okay, it doesn't make sense. So there's a couple things that we can tweak on this. Okay? For these first three that I drew up, HCl, HNO3, and H2SO4, we can kind of cheat with these. Do you know the names? HCl, hydrochloric, HNO3, nitric, this one, acid. Okay, so the name gave it away. That's kind of nice. Okay, there's another reason why you might have those memorized beyond their names. Why did you memorize those names? What's that? Polyatomic ions. That wouldn't give you necessarily that it's an acid. I thought you had to do this in 151. Maybe I'm wrong. Maybe that's 152. When you guys ran acid-base reactions in 151, I'm pretty sure they had you memorize 6 to 7 species. Those 6 to 7 species happen to be the strong acids. Okay? Those three happen to be strong acids. What's the characteristic between them? They all have hydrogen. So we could go through and say that's part of our definition. We've got the hydrogen. We now move to this next species. Okay? This one's a little bit trickier, which is why I included it. How do we know this is an acid? Absolutely has an H. How many H's does it have? 4. Are all of those hydrogens acidic?
No.
No. Okay, how do you know that? Oh, one of them is a polyatomic ion, so we had you memorize some of that. The other thing that we've done in 151 and 152 is when we looked at acids, where did we put that hydrogen? In front. Okay? So for the most part, and I think this is consistent for everything that you'll see in your homework, and I hope exams and maybe in the lecture as well, when running calculation questions, I'll try and make it as obvious as possible if it's an acid or not. Okay? How will I do that? We absolutely have to have a hydrogen, and we'll put it in front of our formula. Does it always have to be in the front? No. If we take a look at that last one, there's another way to write it out. You might see it as well, we don't add a carbon on that. Let's try that again. C2H4O2. Is that a different compound? No, we're still referring to the same thing. Why is the hydrogen now shuttled into the inside? Is it no longer acidic? It's still acidic. So how do you know that that's still acidic? Stick your finger in it, yeah. We don't really have a good option on that. Okay, and we're going to discuss how we can predict some acid-base characteristics based on structure. But formulas, as you'll find when you move into organic chemistry, and if you ever take organic chemistry from me, are useless. Okay? The only way we can determine if a species is acidic or basic from a formula is if we've used some, as far as I'm concerned, BS notation. The hydrogen is in front of the formula. Now it's an acid. Okay? So it's a very narrow application. It doesn't give us a lot of understanding of it, but that's how you're going to see it this semester. Okay, for the most part. Okay? So I want you to be aware of that connection. What happens with our bases? So let's draw up a couple bases as examples. Not very good with bases. Oh, I got a good one. Which of those are bases? Top two you're saying are bases. Why? Oh, I didn't do a very good job balancing that one. That doesn't really matter. Why are they bases? You see hydroxide show up. Okay? So what you're doing is applying our Arrhenius definition. So those top two, I agree. We could look for hydroxide showing up. That is definitely a characteristic of a base. What about the bottom two? Are those bases? Okay, some of you know ammonia. Ammonia is a base as well. Where's the OH? What's that? Not really. Not effectively. It really only acts as a base. Where's the OH? What kind of solution do we work in? We work in a water solution, right? So we take NH3 plus H2O. What happens? So for those of you that know the answer, what do we get? Where's the OH? It came from the reaction with water. We are generating OH minus in this reaction. It's hidden. It's buried. Okay? How did we get that OH minus? What happened? What property of NH3 allowed for the formation of OH minus? Very, very close. Oh, now you're going colder. It had to accept a hydrogen ion from water. For it to accept a hydrogen ion, what did NH3 have to have? What charge is a hydrogen ion? Hydrogen ion is known as by the symbol H plus. What did the nitrogen have to have? It had to have negative. Is there a negative charge on NH3? No. How do we know there's not a formal negative charge? There's no symbol in the upper right-hand corner. So how does NH3 accept? You draw out the Lewis structure, and you notice there's a lone pair of electrons on that nitrogen. That lone pair does have electric charge. It can share with the hydrogen of water and pull the hydrogen away from water, giving us OH minus. So based on the formula alone, can we determine if it's an acid or a base? No. We really have to evaluate the Lewis structure. Okay? There's some simple things that we can jump to with that. We would be looking for nitrogen being a good base because in its neutral state it has a lone pair of electrons. Are there other elements that have lone pair electrons in their neutral state? What's that? Good call. Way to push it to more difficult. Phosphorus does have lone pairs, so that could be basic. I forgot, we're in general chemistry. The periodic table's bigger. Instead of going down, let's go right. Oxygen has how many lone pairs? 2 lone pairs. Oxygen can act as a base as well with those extra electrons. We move further right, what do we get? Our halogens all have lone pairs. Can they act as a base? Kind of a trick question there. No. We'll evaluate why they can't act as a base a little bit later. Okay? So it's not just looking for electrons, okay, or charge. It's trying to make sure that those electrons are on an element that will be willing to share its electrons. Okay? We'll kind of leave you hanging on that thought. So our nitrogen works. So when we're looking at bases, anything that generates hydroxide is a good base. Anything, or ammonia, or derivatives of ammonia, nitrogen in its neutral state will also be a base. Okay, why do I say neutral state? If we drew NH4 plus, what does that act as? Does it have any electrons? No? How do you know it doesn't have extra electrons? It's positive charge. That structure is formally positive. By definition, it doesn't have the electrons to be able to share. Okay? So we'd have to be looking for nitrogen in its neutral state. The next tricky one would be this last one on that list. Acid or a base? We'll do the same thing as we did with the ammonia. We'll add it to water and see what happens. Okay? That species happens to be a solid, so we'll start with it in its solid state. When we add it to water, what do we get? Should it stay a solid? The one rule that I have memorized? 1A, which was group 1 elements are soluble. Where is sodium? Group 1 element, so we generate Na plus and, I already forgot my formula, C2H3O2 negative. That negative could now potentially react with water. Why do we not look at sodium reacting with water? Because it's always soluble. Okay? If it's always soluble, we don't have to worry about it reacting. It's not going to do any of those reactions. Okay? So we could propagate C2H3O2, have that react with water. What happens? What do we need to stabilize the C2H3O2? I heard a hydroxide and I heard a positive. What charge is that species, our C2H3O2? Negative. How do we stabilize that? We want to add a positive. Why do we want a positive? Charge is bad. We want to transfer towards neutral. How do we neutralize a negative charge? Positive. So what are we going to do? We will form HC2H3O2, It picked up a hydrogen from water. What happened to the rest of water? OH minus. What did we just find? OH minus. We just found our base. That was an awful lot of work to propagate through to find the OH minus. Could we find a shortcut in there? Okay, particularly when we go back and look at these. Our sodium hydroxide, our calcium hydroxide, both of those supplied hydroxide immediately, right away. Okay, so both of those would fit under our Arrhenius definition. Under our Bronsted-Lowry definition, okay, to accept H+, what do we need? We need electrons. OH minus has what? Electrons. How do you know it's electrons? Negatively charged. NH3 acted as a base because lone pair, which has our negative charge. Sodium, and I'm going to switch the full name now, sodium acetate acted as a base because it had a negative charge. Okay? So when we're looking for our bases, we could try and propagate these out, put them into water, dissolve them into the ions, react them with water. You're looking at a long sequence of reactions to be able to find that OH minus, okay? Which is one of the reasons why that Arrhenius definition is a bit difficult. We'd have to apply multiple ways out. What's an easier definition to find our bases? What do we need to have? I'm going to switch that up a little bit. We'll call it a source of electrons. Okay, E minus for electrons. Why do I not say negative? What charge was NH3? What charge is NH3? It's neutral. Okay, so we don't want to look solely for a negative charge. Whereas a negative charge is definitely a good source of electrons, there are other sources of electrons, like lone pairs. Okay? So our Bronsted-Lowry definitions, while ultimately give us the same information as our Arrhenius, it opens up the applications a little bit more so that we don't have to go as many steps into the chemistry to find that hydroxide ion. Okay? Further, our Bronsted-Lowry definitions actually work outside of water, whereas our Arrhenius definitions only work within water because we have to generate that hydroxide. Okay? Kind of makes sense? I know, that was a lot of definitions getting thrown at you and ways that we can shortcut it. Okay? So if you're going to look at an individual structure and you're trying to decide if it's an acid or a base, what are you going to look for if it's an acid? H in front of your formula. If you have that hydrogen in front of the formula, probably 99% of the time in this class, we're looking at an acid. If you're looking for a base, you see a formula and you want to determine if it's a base, what should you do? We need to look for a source of electrons. Okay? Some of that may force you to go through and go back to your solubility rules. Hopefully, because I've already said now the only one I've got memorized is that group 1, as soon as you see sodium ion, what does that mean? It's soluble, and we're going to get our ions. We'll get Na plus and something negative. That something negative can now act as a base. Okay? So the intent is that you can now kind of shortcut going through all of those rules. Okay? And some of that is to be able to look at an individual structure and predict its chemistry without having to go through and look at all the numbers. Okay? Questions about that? Okay, I think this next one applies it all. Oh, not quite. More definition. Okay? The next part of this that we'll get is the definition of conjugate acids and bases. So you'll notice we've got two reactions up here. This would be the bisulfite ion. Anybody know what it's called, actually? Good. It's bisulfite. Plus water. Okay? What can happen? I've written it out twice. Why did I write it out twice? You look at bisulfite. What does it have in front? It has an H, which means acid. You look at the end of it. What do you have? Negative, which means base. What's special about this ion? It can act as both an acid and a base. And yes, it does have a charge.
So does the acid have to have a charge, or does it have to be neutral?
It doesn't matter. Okay? So what you need to do is apply the definitions that you've seen. Look for that hydrogen out front. I just realized the one exception to that. I drew up NH4. Okay? On an exam, I will try to remember to draw it as NH3. Whoops. Try that again. NH3 plus. Okay, so that you see that acidic hydrogen on it. I can't guarantee that because that is a very awkward format or notation from standard ways of drawing that, but I will try my best. Okay, that way you can see that that ion is indeed an acid. Okay. So what we're going to do is go through and have these react according to some definitions. So let's say it acts as an acid first. Okay. What does an acid need to react with? A negative works if we want to use the English on it. Acids react with bases. Okay. What's our acid going to do in the course of the reaction? Donate hydrogen ion. What is the base going to do? Accept hydrogen ion. Now that we know these definitions, what we'll do is just follow that English and propagate it through. Our acid must lose H+. So it's, oh, I don't think I got this stepwise nicely. Our base is going to add H+. What's the result? We should get SO3 minus 2 and H3O plus. Okay. In this case, we generate H3O plus, which we said was equivalent to H plus. Okay, so we would then classify HSO3 minus, or our bisulfite ion, as an acid, acting as an acid in this equation. Okay. The next part of this, what does that conjugate mean? Kind of a weird example, but you get conjugal visits, right? Okay, where in theory you've got some relationship, husband-wife kind of a deal. They're partners. So when we go back and take a look at these across the equation, reactants to products, which ones are partners of each other? HSO3 minus looks most like what? SO3 minus 2 or H3O plus? SO3 minus 2 are our sulfite ion. So we would partner those as conjugates. Okay? We're going to take it a step further. SO3 minus 2 would act as what to go the reverse direction, as an acid or as a base? It would have to act as a base because it needs to accept that hydrogen to become HSO3 minus. Right? So we know that that is the conjugate base in our reaction. So our conjugates will always apply on our product side of the reaction, and we'll define them as we would normally acids and bases. H3O plus looks most like H2O. So H3O plus is the conjugate of water, or H2O. Is it an acid or a base? It acts as an acid. It becomes the conjugate acid. Okay? So all we're trying to do is to define everything as we go through and do this. If we looked at our products and only define them as the base and the acid, that gets problematic. Because then when I say which one's the base, well, there's two that would be the base. Okay? So the only reason we introduce the conjugate term is to try and delineate our products versus our reactants. Okay? You should be able to go through and do that next one on your own. And I think we'll go ahead and call it quits there. Okay? Except that next one, when you go through and look at it, HSO3 minus will act as, let's see, does it jump all the way? No. HSO3 minus, have it act as a base. Okay? And go through and predict what you would expect out of that reaction. Okay? We'll start there tomorrow.